UCI in 2015, and he's been working with me for the last, well, 3 years, I think, 3.5 years maybe. Now we have the wonderful opportunity to an outline of the work that he has been involved with me, and so we look forward to that. So if you're all ready, then we should get started. And so the plan, by the way, is to have this presentation for about 50 minutes. And there will be questions. If any of you have questions, I think time to ask. You can also ask questions, of course, as he's doing his presentation, as usual. And then, you know, around one, so in about an hour, the plan is to shut the doors virtually. Then the committee will deliberate about Sunny's fate, which should only take, you know, relatively short time, hopefully, you know, 10 to minutes or so. Now, I think you should go ahead and get started.
Okay, thank you very much, Herbert. And just before I start, can everyone hear me and also see the slides well? Okay, thank you. Yeah, good. So greetings, everyone, and welcome, and thank you for taking the time to join me. My name is Sunny, and I am doing my PhD defense, or as I like to call it, my past 5 years of my life summarized into 55 minutes. My topic will be on cosmological implications of quantum gravity, which is an extension of what my advisor Herbert and I are working on together. So in basically today's presentation, I will go through our work, and it is focused on around a central question that sort of motivated and prompted us to take on this study. We asked the question that how can cosmological phenomena can be connected to any microscopic details of quantum field theory or in particle physics. So I will basically split our talk into 3 parts. I will first discuss what is the basic motivation, what is the mystery from cosmology that prompted us with this particular study, and then I will go through some of the background particle physics that is used in our theory, and share some of our results, some of our unique results that we got over the past couple of years in this area. So we'll start with the cosmology, and the mystery has to do with galaxies. So there's the Sloan Digital Sky Survey, one of the most latest telescopes that scans the sky of the galaxies and create a survey of all the galaxies. And there's lots of measurements of that. And one thing we noticed when walking through this simulation over here is we noticed that the galaxies are not particularly random. They don't get distributed randomly. We'll look at a picture, a snapshot of this in more detail. So we notice a couple of things, first of all. The galaxies form clumps. Okay, so they're not like a complete uniform distribution, and also they form clumps of different sizes. So as you can see from this snapshot, there are parts where there's sparse, and there's parts where it's denser. There are clumps of bigger size, like a huge clump over here, and little small clumps over here. So this is the way that it is in the sky. So we want to ask the question, well, is there a way to quantify these clumpiness in the sky? And there is a way in cosmology to do that. And in cosmology, we use correlation functions, this psi of r, or also another quantity called power spectrum. So I'll introduce a little bit about what that is first for the non-cosmologists in the room. So correlation functions are basically looking at correlations between the sky. So first, let's define a quantity called the density contrast. This is what cosmologists call density contrast, a delta, which is basically just the overdensity at a given point over the average. So it's the fractional overdensity. You take the density at some point and the overdensity over rho bar, the average of the sky. So this is a fractional density. And correlation functions are a way to measure these clumpiness by taking 2 of these objects, like a delta. You pick a point x and I pick a point y, separated by a certain distance r. So that will measure how much overdensity there is in these 2 points. And then now you take an average. You take an average through the whole sky, through the whole volume of interest. So after you take an average with a given fixed r, so you basically take this ruler, in layman terms, move this around and scan the sky with a given distance r. So now what you can do, this is the parameter as a function of r. So what you can do is now vary r. So basically using different sizes of rulers and scan the sky with different rulers and plot a function and see if there's any particular relationship with r. And there is. So this was done by all the way back. This is not new. This is done all the way back in the 60s, pioneered by a recent Nobel Prize laureate, Jim Peebles and Harrison Saldovich, lots of people back in the day. And you see these points sort of lie on a pretty nice little line. And this was first noticed by Harrison, Saldovich, and Peebles, that this follows a nice power law model. So what that means for power law is it can be basically described by two parameters, a amplitude and a critical exponent, so an index over here. And these are some of the early measurements over here. And we see that the value especially will pay a special interest into the gamma, this index, which sort of oscillates around 1.7, 1.8, 1.9-ish. And this actually reminds us of the scaling laws in quantum field theory or even statistical mechanics. So these indices play an important role in quantum field theory or in statistical mechanics because they govern basically how steep the slope is, and it's a particular slope. And this is actually a long mystery since the day of Peebles. So this was some snapshots from his famous book in Cosmology. And it was throughout the whole book, it was a deep mystery of why these values, especially this index, which is believed to be a universally important quantity, takes the value they do. So for a long time, there is actually no solution to this. It was a deep mystery in cosmology. There are different models like fractal models and stuff to try to explain that. But it's not until maybe in the 90s, there was the theory of inflation came along and sort of gave one idea of why this might be the value it is. So our goal, inflation comes with its own baggage. First of all, it's a scalar field that comes with its own baggage, but also there is a lot of controversy from it, even from the creators of inflation, from the fact that there's no unique model. There's some people question its predictability or its flexibility of the theory, which is both a blessing and a curse. So we want to see if there is another way to go about this.
So do we have to worry about that outlying data point?
Good question. Yes, I will actually come to that in a little bit more. Thank you. So keep that in mind as well. That actually represents galaxies over here, which seem instead of the rest of the clusters. So before that, let's look at some more modern data. So that was the early effort. So it remains a mystery all along, right? Until up to nowadays, which we actually measure in P of K. So actually we do a Fourier transform. This is more popular in modern cosmology literature. So you go to the Fourier space or the wave number or momentum space. And this is from SDSS. This is from 2004. There are actually more recent data as well. And instead of quantifying with a gamma or an amplitude R naught, the notation, the standard notation in cosmology is with A naught and S. And from Fourier transform, this is a graduate exercise on the day one of my class to try to show that gamma equals to 3 minus S. So this is the mystery. Summarizing that is, why do galaxies follow this law? Why is gamma roughly like, why does this follow like 1 over R squared? Also, just a notation issue, we also might sort of go back and forth between psi and g. So we'll adapt a particle physics notation where these are Green's functions of correlation functions of g of rho, because we'll reuse psi for a different variable a little bit later. So there is a potential explanation from inflation, but we want to see, can we do better? And we find a different way to look at this.